Hello students. So in the previous video we discussed about step response, and we took some examples on step response, how to find the step response of a signal of a system. Okay. Now moving on to the next topic, uh, we have a Fourier representation of periodic signals. Okay. So it is particularly mentioned as periodic signals because the Fourier representation of a signal, what kind of signal we have to represent in Fourier is important. Okay. So in the previous cases, we defined the system in terms of its impulse response. Okay. That means we find the response of an LTI system only if its impulse response is known. Okay. Now in this case, we have a alternative kind of representing the signals and the systems. So now if you consider the previous methods were only dependent on impulse response. Now in this method we will be considering the complex signals. That means the signals, in some cases they will be represented as a weighted superposition of complex sinusoids. So complex sinusoidal signals. So these kind of signals, it is not uh, better if we use the previous methods. So for this kind of signals, we require a different approach to deal with, because these are complex sinusoids. Now, if you have giving this kind of input to a system, then the output of the system will also be a weighted superposition of each complex sinusoids. So that means we have to consider a new approach. So this is why we consider this Fourier representation of the signals, which will be dealing with the complex sinusoids. Okay. And if you want, this was proposed by Joseph Fourier, the theory for representing the signals. Okay. Now we have certain methods to deal with. That means the basic thing is we have continuous time signals and discrete time signals. Okay. Now Fourier representation can be applied to both kind of signals, continuous and discrete. But apart from that one, we have another kind, that is periodic and non-periodic. Okay. So now this continuous time and discrete time both will have periodic and non-periodic signals. That means you can represent them in discrete and continuous time, both periodic and non-periodic signals. Now for periodic signals, we use Fourier series, and for non-periodic signals, we use Fourier transform. I am writing the short form of that. So Fourier series is for periodic signals, Fourier transform is for non-periodic signals. Okay. So now, as per this, the syllabus is concerned, so here I will be dealing with the continuous time Fourier series. Okay. So continuous time Fourier series here, and we take the properties and we take some examples on that as well. Now, what is this continuous time Fourier series? As the name indicates, it will deals only with continuous time signals, and that too periodic signals. Okay. Now, the Fourier representation, so we call this as Fourier representation of a periodic and that too continuous periodic continuous time signal. So is given by two expressions, okay, or two equations. So first one is x of t is equal to summation k varying from minus infinity to plus infinity x of k e power j k omega naught t. So you can call this as equation 1. Another one is x of k is equal to 1 by t x of t e power minus j k omega naught t dt. Okay. Now these two expressions we use to represent a continuous time Fourier series, okay, for signals with continuous time. Okay. Now here the signal x of t is periodic with fundamental period t, fundamental period t, and the fundamental frequency or you can call this as angular frequency, that is 2 pi by t radians per second. Okay. So these two we have represented what is t and what is omega naught. So this is not w, so this is omega naught here, and this equation 1 and equation 2. So the first equation we call this as synthesis equation, okay, and the second one we usually call as analysis. Synthesis equation, and this one is called as analysis equation. Now what is the difference between these two means? So the synthesis equation creates a continuous periodic signal with the fundamental frequency f. Okay. So how it is done? It is done by adding the cosine and sine waves. So the scaled version of cosine and sine waves will be added together with certain frequencies like f, 2f, 3f, 4f, etc. So these are added here. You can see this. We are using a summation here, and this creates a continuous periodic signal. So that is what we call it as synthesis equation. While coming to analysis equation, so the analysis equation is usually measured for one particular period. That means, as you can see, we have 1 by t, that is the fundamental period, and here the integration is limit to one period itself. So we represent, or you usually write this analysis equation in terms of the period of the waveform. Okay. Now, since the given signal or x of t here, so this will be periodic signal. So it is it is sufficient to take one particular period and just represent one particular duration, how the equation will look like. That means we represent the sine and cosine wave correlation here. Okay. So that's it for analysis equation. Since it is periodic, the sine and cosine wave correlation only needs to be evaluated for one single period. So that is why we represent the analysis equation for one particular period of the waveform. You can take any part, it will be the same because the signal x of t is periodic. So this is about the Fourier series signal representation. Two methods, one will be the synthesis equation and another is analysis equation. Now usually we represent this x of t and x of k. So they are related to each other. How means? So if x of t, goes through, that means if you apply a signal, if you transform this, so x of t is time domain signal, then it will be transformed into another domain, that is frequency domain. So that's why I told you it will be represented in terms of fundamental frequency f in synthesis equation, that is equation 1. Now if x of t is given, you can transform it into x of k, or if x of k is known, you can transform into x of t, vice versa. So for these, we use synthesis and analysis equation to get them. Okay. Now these are related to each other. That means if x of t goes through transformation through Fourier series with the fundamental frequency omega naught, you will get x of k. So x of t is the time domain representation, x of k is the frequency domain representation. Okay. And for this frequency domain representation, we can measure the magnitude of the spectrum x of k, which is denoted by mod x of k, and we can represent the phase of the signal x of t, phase spectrum. We can represent phase spectrum of x of t, which is denoted by phase of x of k. So these two we can represent, find we can find these two for the signal x of t, which is periodic in nature. Okay. So this is the relation between x of t and x of k. Moving on, so we take some properties of Fourier series. I will be representing Fs for Fourier series in short. So let's list out the properties here. So the first one is linearity. Second one is time shift. So third, frequency shift. And fourth one is scaling. So fifth one is time differentiation. Sixth one is convolution. Next, modulation. And eighth one is Parseval's theorem. And the last one is symmetry. So we go through these properties and we take the proof of them. Okay, and it is important to know all these properties of Fourier series. Okay, so let's start with our linearity property here. And in this video, I will be taking some properties and we will take the proof of them. And if not possible in one video, we'll go through the next video for the remaining properties as well. Okay, so let's start with the first property, that is linearity property. Okay, so what does it say? If x of t, so this is just to representing that we are performing Fourier series. If x of t gives x of k and y of t gives y of k after transformation, then z of t is equal to a x of t plus b y of t. So here a and b are constants. You can represent with some other variables like a1, a2, or some other like b1, b2. It's up to you. So I am taking a and b here. So then z of k will be equal to a x of k plus b y of k. So this is the statement. So let's take the proof of this. So a x of t plus b y of t will give z of k is equal to a x of k plus b y of k. So what do we have? We have x of k. How we define f of k? You just take the analysis equation 1 by t x of t e power minus j k omega naught t dt. You can call this as 1. and y of k is equal to 1 by t y of t e power minus j k omega naught t dt. So call this as equation 2. So similarly, how we go with z of k? 1 by t. So here I am representing t means it is one particular duration of t. It may be from t1 to t2, or 1 by minus 1 by minus t1 to plus t1, or minus 1 by t1 to plus 1 by t1. So it's up to you. One particular duration. Z of t e power minus j k omega naught t dt. Now what is z of t? So z of t is a x of t plus b y of t. So let's substitute here. A x of t plus b y of t e power minus j k omega naught t dt. Now if you split this 1 by t, okay, or you can directly since a b are constant in this step only, you can take a and b outside, and it will avoid one more step for you. So a into 1 by t x of t e power minus j k omega naught t plus b 1 by t integral of t y of t e power minus j k omega naught t dt. Now you compare this and this with equation 1 and 2. As we have mentioned here, equation this term is x of k and y of k. So if you come below, this term is equal to x of k and this term is equal to y of k, which is represented as equation 1 and 2. So by this we can write this as a into x of k plus b into y of k. And to the LHS we started with z of k here. So that is what written here. So hence the proof. Okay. So this is linearity property. So next is time shifting or time shift property. So we take the definition of it. So if x of t is x of k, then y of t is equal to time shift, that is x of t minus t naught. So it is given by y of k is equal to e power minus j k omega naught t naught into x of k. Okay. Now this is the statement, and let's take the proof for this one. So we have, so again these things we have to represent. So x of k 1 by t x of t e power minus j k omega naught t dt. So we call this as equation 1. So then what is y of k? Y of k is equal to 1 by t for one particular duration y of t e power minus j k omega naught t dt. So what is y of t? Y of t is x of t minus t naught. So let's substitute that. X of t minus t naught e power minus j k omega naught t dt. Okay. Now in this, since this t minus t naught, I will replace this with some other variable or some other alphabet. So put t minus t naught is equal to m. So that means t will be equal to m plus t naught. Okay. So we have t here which has to be replaced, and dt will be equal to dm, I guess. So let's make these changes. So 1 by t. So the fundamental period will be the same. So x of t minus t naught will become x of n e power minus j k omega naught into m plus t naught dm. Now here we have m plus t naught for this term. So we have to perform multiplication for this term, and we get two exponential terms, and with respect to this dm, one will become constant. So let me do that step and it will be easier for you to understand. X of m e power minus j k omega naught m e power minus j k omega naught t naught dm. Now with respect to this term will become constant. So we'll take that outside, e power minus j k omega naught t naught into 1 by t integral of x of m e power minus j k omega naught m dm. So now the second term, this term, you just compare with equation 1. Everything is same except we have t here, and here we have x of m omega naught m with respect to dm. So that means this expression is nothing but our Fourier series expression here. So that's why we can replace that with x of k. So this e power minus j k omega naught t naught into x of k. So to the LHS we started with y of k. So hence the proof here. So this is what we are supposed to prove. So that's what we get here in the end. Okay. So this is about time shift. So the next one is frequency shift. So let's take the definition first. If x of t will give x of k, then y of t is equal to e power j k naught omega naught t x of t. So this, after performing Fourier series, what we get as y of k? Y of k is equal to x of k minus k naught. So this is the statement. So here you can see this, we are performing frequency shift. So that means the shift will be happening in frequency domain. So now how to get the proof, check whether it is happening or not. So again we start with the first signal x of t, sorry, x of k. So call this as 1 here. Now y of k is 1 by t y of t e power minus j k omega naught t dt. Now substitute y of t. So what is y of t? Y of t is e power j k naught omega naught t into x of t. So this is our y of t here. This is what I have substituted here. So into e power minus j k omega naught t dt. Now these two have the common base here, and we can combine them since both of them are having common base e. So x of t e power minus j. So observe here I am writing omega naught t first, and then here we have plus k naught, and here we have minus k with respect to minus j here. So to get this I am writing this will be equal to k minus k naught. So minus into minus become plus, we will get the same term here dt. Okay. Now this is my y of k. Now compare this with equation 1. So we have x of k, so that means e power minus j k omega naught t. So here we have e power minus j omega naught t, but in place of k we have k minus k naught. Now comparing this with equation 1. Okay, so comparing this with equation 1, you can see x of k will give e power minus j k omega naught t. In the same way, if you get e power minus j omega naught t k minus k naught, then it will be the time shifted version of that in frequency domain. So that is x of k minus k naught. So this is the proof. Once we get the point where y of k is equal to x of k minus k naught. Okay. So this is a frequency shift, and let's take the next property, that is scaling. So the definition says if x of t gives x of k, then z of t is equal to, you can write z of t or you can write y of t, it's up to you. Z of k is equal to x of k. So scaling. So in frequency domain it will be the same. Here we have a small catch here. We are performing scaling operation. So that means the fundamental period will not be the same for these two. So how I'll represent this here. So if x of t has fundamental period t, then x of at, then x of at will have fundamental period as t by a. Okay. So therefore, if fundamental period becomes t by a, then our frequency, that is angular frequency or fundamental frequency, of x of at is a into omega naught. So that means here the Fourier series will be performed with fundamental frequency a omega naught. It's not a comma, it's a into omega naught, a into omega naught. So this is the major difference. Okay. Now let's take the proof of this. So x of k is equal to 1 by t x of t e power minus j k omega naught t dt. So call this as equation 1. Next, so what is z of k? Z of k is integral of z of t e power minus j k omega naught t dt. So now what is z of t? Z of t is x of at e power minus j k omega naught t dt. And here, as I mentioned, this omega naught for x of at will be a into omega naught. So that's why we have to write this as k a omega naught t, and the same applies here as well, k a omega naught t. Okay, so this is the frequency for x of t. The fundamental frequency is omega naught, so that's why we have omega naught here. For z of k, because the fundamental frequency is a omega naught, so we have represented like this. And one more thing is, this fundamental frequency will 1 divided by t by a, and if you simplify this, this a goes to numerator, and we will get like a by t here. Okay, so now I will replace this with some other variable. Let's see what happens. Put a t is equal to m. So if I put a t is equal to m, then here you observe this a and t is there, so that will be replaced by m, and this at will also be replaced by m. Then what happens to dt? So dt will be 1 by a dm. Okay, so dt will be 1 by a dm. So let's substitute all these terms here. So integral of t, x of at will become x of m, and e power minus j k. So I'm writing omega naught first. This a and t combined together, I can replace this with m into 1 by a dm. Now this 1 by a is a constant, we can take it out. A by t into 1 by a integral of t x of m e power minus j k omega naught m dm. So a get cancelled here. So we remain with 1 by t integral of x of m e power minus j k omega naught m dm. So this is nothing but comparing with equation 1. So this term is nothing but our x of k only, which is represented in terms of m here. So that's the only difference. So therefore we can write it as x of k, and here we have zk. You can take any other variable like y of k if you want to. So this is the proof, hence the proof for scaling operation here. So I don't want to make this video much lengthier. I will stop the property here. In the next video, we'll continue the properties, and we'll go through the statement and derive, and we'll get the proof of it. Okay, that's it for this video. If you have any queries, or you can comment in the video, or you can reply me. So thank you for your time.